In this video, we're going to look at the concept of projectile motion. What are we going to do? We're going to define what a projectile is. We're going to compare projectile motion to freefall motion. We're also going to look at the properties of a projectile motion. And we're going to look at problem-solving strategies that can be used to solve projectile problems. Why are we doing this? Because many objects move as projectiles. Projectile motion is in fact an extension of all the other motion types that we have learned so far. And if we understand this connection, then this insight will make our ability to make predictions about how objects will travel as projectile much easier. Many people who do not have this insight struggle greatly with this motion. Projectile motion does have several different things happening at the same time, as in most situations in life where you don't have one problem, but many problems that we have many different moving parts and events happening. Most people have difficulty breaking situations with many moving parts into smaller, easier to work with problems. So this is a skill that we will develop that will transition to problem solving for other real world, real life issues that we will also have. So the thinking skills needed to solve problems with simultaneous events of one type also apply to other types of problems that also have many different things happening at the same time as well. Not all motion is projectile motion. Some of the classic examples that we'll see is a ball that is tossed into a basket. If you take a look at the water coming from a water fountain, we often see that as a projectile because a projectile moves, in fact, as an arch. But if we think about this, there's no propulsion of the motion with the exception of when the object is first thrown. And the only force acting on the ball while it's in the air is, in fact, the force of gravity. The only force acting on the water as it is moving is, in fact, the force of gravity. And that is incredibly significant. The reason why it is significant is because a projectile really is a falling object. Here we can see a little video of a ball that is dropped and a ball that is thrown sideways at the exact same time. At all points, the two objects have the exact same height. This is only possible if the object that's moving sideways is falling at the same rate as the object that is dropped directly. Here, we actually have pictures of these objects as they are traveling, and we can see that the yellow projectile ball, in fact, falls along the y-axis at the same rate as the falling red ball. In fact, the y distances follows the rule of odd numbers. This is one of the two reasons why projectiles have a parabolic path, because the y motion does in fact follow the rule of odd numbers because it's a falling object. And I personally always think of a projectile motion as a falling object, at least for the y motion. But projectiles don't have just y motion like a falling object. It also has motion along the x-axis. So this is why we call it simultaneous events, because I have two events happening at the same time. I have a falling event going down, and I have an x motion event happening at the same time. This x motion, though, is incredibly simple. If we take a look at pictures of old bombers, and you often see bombs from the plane, you'll often notice that the bombs, even when they have fallen a long distance, are in fact directly underneath the airplane. That's only possible if the bombs are moving forward with the aircraft after they've been dropped at the same rate that the aircraft is actually moving. Here we can actually see people jumping out of an airplane. And if you notice, there's the airplane wing behind them. And this airplane wing never hits the people. In fact, they stay the same distance from the airplane wing as they are traveling through the air as they were when they first jumped out of the airplane. This is only possible if the people are moving forward at the same velocity as the airplane wing is moving. Remember, Newton's first law of motion. Objects in motion tend to stay in motion with a constant speed and direction unless acted on by a net external force. If there is no external force pulling the projectiles forward, then they will have the exact same motion forward as when they were released as compared to when they fall. That means they will have the exact same motion forward as before they were released, which is the motion of the thing that dropped them. So all projectile motion consists of two types of motion. For the y-axis, it's an object that is simply falling. It is free fall motion. It has one force of gravity pulling down. We know the acceleration, and we solve it exactly like we did with free fall. And we have x-axis motion at a constant velocity, which was the most basic motion and the first type that we actually looked at. If you remember when we first looked at free fall motion, we had discussed how free fall motion was very symmetrical, where the motion on the way up and the motion on the way down are identical as long as you are released when you're fired and land at the same height. Well, since projectile motion is in fact free fall motion, we have that same kind of symmetry, where the time it takes for a projectile to reach maximum height is the same amount of time as it takes to fall downward. But since the x motion is at a constant velocity, and the time up is equal to the time down, then the distance I travel along the ground for the first half of the motion has to be the exact same distance traveled on the second half of the motion. Also, just like with a object thrown straight up and straight down, we have symmetry of speeds. We also have symmetry of speeds for the projectile, where the speed at any given height is equal to the speed on the way down at that same height. Please notice I'm saying speed and not velocity. Velocity has a direction as well as a magnitude. If I take a look at B and H, B would definitely be moving in an upward angle direction. H is in a downward angle direction. So they definitely cannot be the same velocity. But the magnitude of the velocities, or the speeds, will in fact be the same. At all points of the projectile motion, from the point on where it has left the launcher to the point where it lands, just before it lands on the ground, the acceleration is the acceleration due to gravity for the planet or moon that you are on. Remember, if we don't specify what planet you're on, or if you're on the moon or something, we default to the planet Earth, and the acceleration of gravity for Earth is considered to be 9.8 meters per second squared downward, or if you prefer, negative 9.8 meters per second squared. The projectile will always travel fastest at the extremes. So if I have symmetry of motion where I am fired and land at the same height, then I have the greatest speed at the time of launch and the time of landing. The slowest will always be at maximum height. One of the reasons for this is I only have a velocity for one axis. That's going to be the x-axis, because for an object that's thrown straight upward, the velocity is 0 at maximum height. If I focus on the velocity vectors of a projectile while it's in the air, I can break my velocity vector into two components, the y motion and the x motion. Please notice that the x motion vector never changes in terms of direction or magnitude. And that's because the velocity for the x-axis is a constant. That means the acceleration for the x-axis is 0, and it will never change. So if I can see my x-axis motion for just one spot, I know it for all spots. However, the y-axis is always changing. If I am moving upward, my acceleration will cause my velocity to become smaller to a point where it eventually stops. And it will get smaller at the rate of the acceleration of gravity for the planet or moon that I'm on. Again, for Earth, that would be 9.8 meters per second squared. I would be slowing down at because gravity is going to pull me opposite the velocity. However, once I get past maximum height, the acceleration will now make me speed up at the exact same rate it cost me to slow down, again providing that symmetry of motion. Please notice at maximum height, I do in fact have a velocity. I do have a speed. It's not 0. It is 0 for the y-axis, but I still have an x-axis motion. So a lot of times people get confused because they don't clearly state what they're talking about. And so they'll go, oh, at the top it stopped moving. No, it stopped moving for the y-axis, but not the x. Thus, it still has a velocity. Here's a famous situation that I want you guys to think about. So after we go over the question, pause the video for just a moment, think about what your answer would be, and then simply play the video or continue the video. Here we have a huntsman that's in the jungle and they see a monkey that's hanging from a tree limb. So the monkey is just hanging on with like one or two hands, and the hunter raises their rifle to shoot the monkey, and they aim directly at the monkey. Now, the very moment the bullet is fired from the barrel and it leaves the barrel, the monkey lets go and drops out of the tree. My question is, will the bullet hit the monkey where it intended? If not, will the bullet be too high or too low? So will the monkey drop out of the way, or will the bullet still be lower than the monkey when it gets to that location where the monkey would have been? So again, simply pause the video for a couple of seconds, just think about what your answer is, and then simply continue playing the video. Here we have a scenario that we can see as a simulation because we're not going to actually shoot a monkey. Here I have the gun that's going to fire this little white disc towards this other disc that starts up right here at the very top. That's going to be our monkey. If you notice, the moment that the disc is thrown, this object up on top falls. That's because there's an electromagnet at the very top that is connected to the gun. The moment this little disc is fired from here, it breaks the current to the magnet, causing this guy here to drop. Please notice that the disc constantly hits that falling object. So the truth of the matter is, if the monkey had just held on, the huntsman would have missed the monkey. Now, if you do anything with any type of target practice, we all learn that when you aim to hit a target, you don't aim directly at the target. You always have to aim a little bit above the target. And that's because gravity causes whatever it is that you're throwing to fall. So every time you aim at the target, you would miss. It would be too low. The monkey, because they let go, gets hit because they're falling like the projectile that was fired. You see, this huntsman wasn't very good at their job, and they were thinking as if there was no gravity. And the truth is, if there was no gravity, then that bullet would travel in a straight line as as the bullet was, as the rifle was pointing because of the law of inertia. The gun gives the bullet a velocity which has a speed and a direction. And if there is no external force acting on it, such as gravity, then the velocity of that bullet would remain constant, with a constant speed and a constant direction, so it would simply hit the monkey exactly where he's at. But since there is gravity, that would have to arc down and it would miss the monkey if the monkey held on. If the monkey let go and there was no gravity in the situation, the monkey's going to get hit because the monkey's not going to fall when he let go, because he is at rest and will remain at rest because there's no external force acting on the monkey, because there is no force of gravity here. However, when there is gravity, as there always is, the monkey gets hit. We have what's called a line of sight. This was the path that the bullet would have traveled had there been no gravity. Since there's gravity, the bullet falls away from this line at a rate of the acceleration due to gravity, which is 9.8 meters per second squared on the planet Earth. But at the same time, the monkey also accelerates away from the line at the same rate. So in 1 moment's time, whatever distance this is the same distance here that the monkey fell. Whatever distance this is, that's the distance that the monkey fell again from the line. So this causes the bullet and monkey to be the same height when they meet, and so the monkey gets hit. This is not at all intuitive unless you think of the line of sight and that both objects are accelerating away from this line at the same time. You can think of it then as two people who are on a race. We start on the same starting line and we both launch off and we run with the exact same acceleration. Who's going to win the race? It's going to be a tie. That's exactly what we have here. One of the terms you're going to hear a lot with projectile motion is something called range. Most people get confused with this in the very beginning because one of the places you often heard the term range is your math class. But not all ranges are the same. In math, you often define the range of a function as all the possible values of that equation. So if I had an xy axis, and I was to turn around and have a graph such as y equals x, then my range would be from negative infinity to positive infinity, and because those are all the possible answers in between that I could get. But that's not what we're talking about with projectile motion. In fact, many people also start to think that range for projectiles has something to do with height, because, well, that's like up and down like the y-axis, and when I do my math class, my range is all about the y-axis. And again, that is totally and utterly and completely inappropriate. I will not say it's wrong, because for math, that's what a range is. But when we're talking about projectiles, it has nothing to do with values of a function. There's no function here. We just have a kid who's throwing a ball to this grown-up. Now, if the ball goes up and goes down, lands here, we would say that this person is out of range of the kid's throw. That's because range is the distance the projectile travels along the ground. So if the ball only travels from the kid to this spot, then the range would actually be this. And this individual is not in the range, so he's out of the range, so he's out of range. If this ball travels past the person, then they are definitely in the range of the ball. So they are now in range of the kid. The kid just didn't hit the person. And if this ball lands exactly where they're at, then that person is, again, in range. So range is only about the distance traveled along the ground. Again, people get confused on this going, well, that's the x-axis, and I thought it had to do with the y-axis. That's not exactly true because there is no xy axis on any of this stuff. In fact, if I was to graph positions here, I would have x positions, but this x-axis would be my time. If I am doing a graph of my y values for position versus my x values for position, I should see a parabola just like the path here, because that's exactly what we have. These are my x-axis positions along the ground. These are my y-axis positions up in the sky. So again, range for us will only be the distance along the ground only. Some people get confused with the term range and trajectory. Trajectory is the actual path that a projectile travels. We are never interested actually in the values of this. Too many things are happening. I'm accelerating along one axis. I'm moving across another axis at constant velocity. This is very complicated. Not only that, but often I just want to know how high is something when it stops moving, how far over. The actual path is inconsequential to where did it end up. So it's nice to know what trajectory is, but we're not going to really worry about it. We're going to worry about heights, and we're going to worry about range. The angle at which you throw a projectile will always affect the range that the projectile can travel. If I start throwing something perfectly horizontally, it will go a certain distance, which will be rather short. If I start tilting the angle upwards, however, the range will start to increase because the object will have more time in the air as it has to travel up a bit than to fall back down, thus having more time to travel. However, if I make the angle too great, then the ball spends a lot of time in the air, but it's not moving forward very quickly, and so the range will actually get smaller. The angle that gives you the largest possible range, if there is no air resistance, is 45 degrees, which is the exact middle from 0 to 90 degrees. It's also important to note that my range can be duplicated. Often when I have two angles will give me the same range. Those two angles always add up to 90 degrees. They're always complements of each other. So if I fire a projectile at 30 degrees and another one at 60 degrees, they will land in the same place, provided that the speed that they were both thrown at was exactly the same. So if I launch a projectile at 100 meters per second at 35 degrees, it will land in the exact same spot as if I launched 100 meters per second at 55 degrees. We're not going to say they're going to get there at the same time. They will get there in the same place. The one fired at 35 degrees would get there first because it's going to travel faster along the ground. The other one will take longer to go, but will get in the same spot. You'll often see this in sports such as tennis, where the athletes start to fall into a rhythm. And then all of a sudden, one of the tennis players will lob the ball. All of a sudden, the ball is going to land in the same spot as it did before, but the ball's going up high. And the purpose of this is I set you in a rhythm where it's back and forth, back and forth, back and forth, back and forth. Then all of a sudden, I lob the ball, and then you're in a rhythm, so then you go too fast and you miss. And they want to lob the ball back into the same spot because if I now have to adjust my position, there's a mental reset and I will not fall for the timing trick. So this is a classic thing that you'll start to see. If you watch movies where you're dealing with a whole bunch of archers who are going to fire on an oncoming army, you often see the archers fire in two phases. The first one is arrows that are being lobbed very high, and they go high in the sky and they're moving kind of slow, and the oncoming army sees it so they can raise their shields. But then all of a sudden you have another set of arrows that are now fired at a smaller angle. That's the complement of the angle being fired that was first fired. So now all of a sudden these arrows come in very quickly and they're going to land in the same location. So now all of a sudden I have a choice. I can either block the arrows from top and get hit in the chest, or I can block the arrows coming in at my chest and get hit in the head. Either way, the archers are fine because their arrows are going to hit their targets. And so again, they fire the ones that are high up first because they're going to take more time to get there, so they get a head start. That's when they fire the second round at a lower angle, because they will travel that distance in a shorter period of time. So they get now there at the same time, since the slower arrows had a head start. So again, here we have the ranges for different angles. And I can see that 75 and 15 land in the same location, but the 15 angle definitely would get there a lot faster than the 75. The reason for this is the values of sine and cosines flip for complementary angles. The cosine of 75 is equal to the sine of 15, and the sine of 75 is equal to the cosine of 15. The angle that will give us the longest possible range is 45. And if you think about it, what's the complement of 45? It's 45 itself. And the two angles that will give you the smallest possible range is 0 degrees and 90 degrees. And that makes sense if you think about it, because if I am on the ground and I kick the ball across the ground, it never leaves the ground. So it has a range of 0. If I kick the ball straight upwards, then it will fall straight back downwards and will land exactly where it was launched from. So again, it has a range of 0. If you're ever asked which of the following angles gives you the longest range, whichever angle is closest to 45 will always give you the longest range. When trying to solve these problems, I'm going to have motion along both the X and Y axis. I'm going to have two events happening. This is going to be very similar to when we had boats trying to cross a moving river, because I had motion along both the X and Y axis. So we're going to use a very similar method again. We're going to be using a T-chart. Again, the first thing we want to do is draw the situation so we can get a visual. We're going to break everything up into components, especially my velocities when I'm fired at an angle. So I'm going to draw out any velocity that is at an angle. I'm going to draw it as a right triangle where I'm going to label the X and Y values, and I'm going to solve them using sine, cosine. Remember, we can always use sines and cosines to break my vectors up into X and Y components. The next thing is I'm going to organize my information. All my X information goes on one side of my T-chart. all my y information goes on the other. Again, they will not tell me often because I will know what the accelerations are. For the x-axis, acceleration is 0. If it's not 0, I'm not really a projectile. For my y-axis, it's going to be the acceleration of gravity for wherever I'm at. And again, normally, negative 9.8 meters per second squared for us on Earth. Because again, a projectile doesn't fly. Projectiles are a falling object. Once I have this set up, I'm going to simply solve whatever you're being asked to solve for. And sometimes I'll have to solve for something first to get to what you're being at, whatever you're asking me about. And often that will be the time. So here we have one of the most basic of all the projectile problems, an object that's going to roll off a horizontal surface. If you notice, I don't have a right triangle for my velocities. So I have a ball that's going to roll off a 4.9 meter tall table with a speed of 3 meters per second, and I want to find the range of the ball. Again, range is going to be my x-axis motion. Please notice I have a diagram here where I have an origin and I have my initial positions and final positions, both x and y values. I got that from the height that I was given. I picked my own origin. I could have picked up here to be my origin, but I personally don't think that having my origin up at top is very convenient. I like my final height to be often 0. So I often pick the ground to be where the origin is and the starting point of the projectile to be in line with that. I have my velocity, that's going to be 3 meters per second, and that's going to equal Vx. And Vy is 0 because it's horizontally thrown. There is nothing going up and down. So now I'm going to take my information and I'm going to organize it on my t-chart. All my x-axis information goes on one side, all my y-axis information goes on the other. Please notice I know the acceleration for the x was 0, as it always will be for us. That's 0 meters per second squared. My initial x velocity was 3 meters per second because my velocity here is going along the x-axis. My initial x position was 0, and my final is unknown, so I'll just call that range. For the y-axis, it is a falling object, so my acceleration is the acceleration of gravity, negative 9.8 meters per second squared. I don't have a Vy, all I have is a Vx, so Vy is again 0. Anytime something is fired or thrown horizontally, Vy initial will be 0. My initial y position is positive 4.9 meters, and my final is 0 because it landed on the ground, and I declared 0 to be the ground. I'm looking for range, which is position, so I'm going to work with the position versus the position equation. I know my initial position is 0 for the x-axis. I know my initial velocity is 3, and I have an acceleration of 0 for the x-axis. This equation reduces down very easily to range is equal to 3 meters per second times t. So all I have to do is take the time, multiply it by 3, and there's my range. Problem is I don't know the time. I have to solve for it. This is the same scenario that we had when we had the two-dimensional uniform motion where you had boats crossing rivers. So just like there, I'm going to just simply look at the other side of my t-chart. In this case, I have to look at my y-axis motion. For the y-axis, I know my initial and final positions. I know my initial velocity, acceleration. I'm looking for time. So again, I'm going to have to use the position formula. This one looks a little bit more intimidating because I'm going to have to plug in these numbers, but it simplifies very easily. I have 0 equals 4.9 plus 0t plus 1/2 negative 9.8 t squared. But this is just 0. Anything times 0 is 0. 1/2 of negative 9.8 is negative 4.9. I'll take this 4.9, slap it to the other side. and I can easily solve for my time, which is 1 second. Once I have that time, I can plug it back into my x equation, and I find the range. Here we have a question that's going to be a little bit more involved. Here the object is being fired at an angle. So I will have both an x velocity initial and a y-axis velocity initial. Please notice that I'm going to set my origin to be the starting point of the ball, where my initial values for both x and y are 0, 0, because the object starts on the ground. Please notice that the final height of the object is 0. It lands on the ground. The x final is not 0. That's the range, and I just don't know what it is. This question looks different from the first problem, but it really isn't. The only thing that's really different here is I have a vector that has a magnitude and an angle that's not 0. So I'm going to break that velocity up into components using cosine and sine. So 20 cosine 30 gives me a Vx of 17.32 meters per second going to the right, and Vi is going to equal 20 sine 30 at 10 meters, is equal to 20 meters per second times the sine of 30. So that gives me a VIY of positive 10 meters per second. I want to make this very important. If this was somehow being fired downward, so if this was like on a cliff, I fired this down at 30 degrees, then VI would be negative because it would be going downward. But in this case, it is positive because it's being kicked upward. I will now go ahead and use my t-chart. The acceleration for the x is still 0. VI was 17.32. My initial x position was 0. And my final is range. I don't know what it is. For my y-axis, I have the acceleration of falling, which is negative 9.8 meters per second squared. My initial y velocity is positive 10 meters per second. My starting height and ending height are both 0. And since I'm looking for range, which is a position, I'm going to use the position formula for the x-axis exactly like before. And again, I get the same setup as last time, where I have range is equal to my initial velocity times time, initial x velocity. And this is what you will always get for the x side of this setup, because the range will equal my x initial velocity times time, because there is no x acceleration. And just like before, I can't solve this because I do not know the time. So just like every other situation, I'm going to look at the other side of my axis, where I will use the y side. This case, my algebra is a little bit more involved. I have 0 equals 10t plus negative 4.9t squared. Now, there's two ways I can solve this. One is bad math, where I can bring the 10t to the other side, divide both sides by t, so they cancel out a little bit, and then I can go ahead and solve for t by dividing 10 by 4.9, and I come up with an answer. Now, the reason we call this bad math is because there are actually two t values that will give me 0. If I was to actually factor out my t, I would get 0 equals 10 minus 4.9t all times t. And now I could turn around, split this out, and solve for two equations. The first equation would be, in fact, running it up here so we have a little bit more space. 0 equals 10 minus 4.9t. So I could solve for t and come up with 2.04. But my other equation is 0 equals t. And that is useless to us. Yes, T equals 0, I had no height. So I'm not interested in that one. So if you turn around and do this math here where you're just bringing the 10t over and then canceling out the t's a little bit, we are not going to be angry and we're not going to judge. Your math teacher would turn around and be very bothered with this because you're negating one of the answers. You're negating something that we don't want. So this is a practical thing to do. Just be aware that mathematically it's a bit of a no-no. So we just want to point that out. You can solve this however you see fit. And you could also turn around and say the following. You could turn around and say A is equal to negative 4.9. Let's say capital A is equal to negative 4.9. B is equal to 10. C is equal to 0. And you could turn around and use the quadratic formula where negative B is equal to plus and minus the square root of B squared minus 4AC all divided by 2A. And you will come up with two answers. One will be 0 and the other one will be 2.04. So it doesn't matter what route you take, they will always be accurate and acceptable. And you're going to just take the time that's not 0, plug it in to solve for the range. One of the other things that we can do to throw you guys off is instead of asking for a range or a height or position, we'll turn around and ask for a velocity. Now, we're going to solve this the exact same way in terms of strategies, but we will have to use a different motion equation. And the question is, which motion equation works best? So here I have a ball that's going to be thrown off of a cliff that's 20 meters high with a velocity of 50 meters per second at an angle of 20 degrees. They're not specifying if this is above or below the x-axis, but from the diagram, we can see it's above the positive x-axis. So Vy will be a positive for the initial y velocity. Had this been below the x-axis, then my initial Vy would be a negative. But again, it's above the positive x-axis from my diagram, so I'll have a positive y velocity for the y-axis. So I'm just going to use 50 sine 20 for the y value. I'll make sure that it's a positive. 50 cosine 20 for the x-axis. I know the accelerations for the x are always 0 for projectile, and its gravity, which is negative 9.8 meters per second squared for the y-axis. I'm looking for my velocities. So I'm going to find my v final x and my v final y, and I'll just simply find the resultant by using vectors. And since I'm looking for velocities, I'm probably going to start with my velocity equation. It's velocity, it's small, it's simple, it's going to be beautiful, I'm going to use it. And for my x-axis, I have 50 cosine 20 plus 0t, so my Vx is equal to 46.98, which was the exact same initial velocity that I had because there was no acceleration. For the y side, I'm going to go 50 sine 20 degrees, which is actually 17.01, plus negative 9.8 t. I actually can't solve for this velocity because I do not know the time. I'm being blocked. Now, I do have an option. This is very much like our first problem that we looked at where an object is fired. Actually, this is very much like our second question where an object is fired at an angle. So I could use my position formula to solve for the time using the y-axis. So I can turn around and say in the end, using my y-axis motion, that a height of 0 equals 20 plus 17.1 t minus 1 half negative 9.8 is 4.9 t squared. This is a quadratic. And I will have to use the quadratic formula to solve for the time. Once I have the time, I can go ahead and plug it in. The quadratic will give me 2 times. In this particular case, I'll have one time that's positive, one time that's negative, because mathematically, I would also have a 0 back here, but that never existed, so it doesn't make sense. We never use a negative time. It's not physically there, though mathematically, if you were to travel back in time and extrapolate the path and ignore the platform, you could do this. That's ridiculous. So we ignore any negative times. Now, if you're going, wow, quadratic 2 times, I have to throw one out. I think I'm dying inside. That's totally okay because I don't do this. Please notice I'm going to be merging a problem with the velocity equation and the position equation. Every time we merge those two equations together, we get the time-independent formula. And since I don't have the time, I'm going to work independent of it. So I still have the exact same information as before. y is still 50 sine 20. Vix is still 50 cosine 20. The acceleration for the x is still 0. Y is negative 9.8 meters per second squared because it's gravity. And when I go ahead and use the time-independent formula for the x-axis, the acceleration is 0. And I come up with Vx final squared is equal to 46.98 squared. So when I take the square root of 46.98 squared, I do not get 46.98. I get plus and minus 46.98 because there are two possible ways this thing could go. Looking at the situation, I see this object can only be moving to the right. So I'm going to turn around and say this is positive because there is no negative direction in this problem. Everything is moving to the right. When I look at my y-axis, this is now very solvable. I have 17.1 squared, which was my initial y velocity, plus 2 times negative 9.8, which is negative 19.6, times the change in the y position, which is 0 minus 20, because it's always final, which was its height of 0, minus my initial, which was 20. I can totally solve this. I come up with plus and minus 26.16. You see, it's not or. Both are possible answers. However, looking at the problem, I can tell that this object can only be going down because it's off of a platform and it's landing on the ground. So I'm going to turn around and say that this is negative 26.16. I have to use my own intelligence and my own awareness of the situation to decide what sign these should be. The time-independent formula never gives you direction. You have to look at the situation and use your own intelligence to determine what that direction is. It's never hard. Anyone who just thinks about it never gets it wrong. I now have an x and y velocity, so I'm now going to draw out a right triangle, and I'm going to do Pythagorean theorem and arctangent to find the angle. If I want to, I can use a ruler and protractor, and as long as I draw this out to scale, I will be able to measure this out as well. Keep in mind again, when solving for this angle, do not use the negative sign. Say theta is equal to the arctangent of my opposite, which is 26.12 over 46.98. Because again, your calculator does not recognize 4 quadrants. It only thinks there's 2. If you put in the negative, it will give you an angle that might be the wrong sign that could be very confusing. So you're looking at the magnitude, and then you can look at the situation and go, well, that's below the x-axis, positive. So I'm going to turn around and say it's at 29.7 degrees, 29.07 degrees below the positive x-axis. All right, that's going to wrap us up. Hopefully this is making some sense. If you're looking at this and going, I got this is really nothing new, you are ahead of the game. You're going to have a very easy time in class. If you're looking at this going, I kind of get it, but I really hope we have some more practice and some explanation, you're exactly where you need to be. If you're looking at this going, I'm not feeling very good right now, nothing to worry about. As always, we have time to work on this. We just wanted you to get exposure to this stuff, and that's exactly what you've done, and I thank you for that. And remember, these videos are never intended to get me out of my job and teach. This only gets you exposure to the information and concepts before we actually use it in class.